And I think I'm going to do this with drugs and behavior as well, for obvious reasons. Okay. All right, we good. All right, so I will email you this after class, probably when I get done with work and when I get home. And I'll try to make sure Smedley doesn't crawl all over my laptop, and I'll send you links to this. These are going to take some time to process anyway, so just be aware of that. All right, so the last time we were here, we were talking about precision for planning. I think these little things are about to snap on my mask. I'm worried the little nose protector is about to snap. Let me tighten this up just a little bit. If worse comes to worse, I'll get my my disposable paper ones later. Yeah, that's much better. Okay. Somebody keep an eye on me and tell me if my nose is starting to fall out. I don't want that. Okay. So the last time that we were here, we were talking about precision for planning and basically the idea that you have to think very carefully about what kind of study design you want, how many people should be in your study and things like that. So I want to kind of walk through an exercise. So we'll have an opportunity to really practice what we've learned with our precision for planning. So Angela, not my friend Angela, but just an Angela wants to develop a research project to complete her degree with honors. So usually what you have to do with honors, it's kind of like an independent capstone here at Coady, except that with an honors thesis, you usually have to defend it in front of 3 professors, like it's a master's thesis, and it's really terrifying. I've done it, can confirm. She has 3 different fields of study she can choose from. One possibility is based on using hypnosis to influence the Stroop task. Okay, it is a between subjects design that will require 4 groups with each participant completing a 1-hour session. The basic Stroop effect is large, and it's estimated that the population D prime is 0.9. Another option is based on using economics education to influence sunk cost effects. So for those who may not know, the sunk cost effect is basically when you continue putting time, energy, resources, things like money, into something that is not really working very well anyway. So you continue to put money into a car that keeps requiring repairs, which is actually what I was doing with my cruiser before I got a new car. It is a between subjects design that will require 4 groups with each participant completing a 30-minute session. The basic sunk cost effect was recently estimated to be a moderate effect, with Cohen's D in the population being 0.3. A final option is based on using social cues to alter the norm of reciprocity effect. This study can be run as a within subjects design, with each participant completing a 2-hour session. The norm of reciprocity was recently estimated to be a moderate effect, with this being 0.3. When run as a repeated measure, typically R equals 0.75. You will need to modify the truncate display settings in ESCI to obtain a sample size. So to complete this activity, you are going to need to use precision 2 and precision paired. This will allow the selection of target margin of error in 0.05 increments. And when we're planning for a target margin of error, we're going to go ahead and round down to the nearest 0.05. Using the very general rule of thumb. So the rule of thumb is that you want a margin of error that is half as big as the expected effect size. Help Angela plan a desired sample size for each potential study using assurance. Yeah, this mask is officially done. It is one of my older ones, so I'm gonna go run to my office really quick and switch into my disposable one, so I will be right back. Because I keep fiddling with the nose and it's gonna slip. Thanks, folks.
That's what I feel like each time I hear someone's heart, it like becomes more. Yeah, I feel like sweets or chicken and there we go.
That's a little bit better. I at least feel like my nose has better odds of being protected this way. There we go. I also feel like I could be a physician with this, but I know I couldn't. I'd pass out if I saw blood. So the general rule of thumb that we want for planning here is we want a margin of error that is basically half the size as the expected effect size. So we're going to go ahead. I'm going to go back here and I'm going to pull up Esky. Old pesky Esky. Okay. Give me my Esky. Oh, there we go. It kind of needs to be here. Okay, so we want Esky. So we want our Esky chapters 10 through 16. So I'm going to go ahead and pull that up. Ta-da! We're going to go to precision 2. So we're going to start with our between groups designs. So we're going to go ahead and start with the Stroop effect. So the basic Stroop effect is large. It's estimated that the effect is a population Cohen's d of 0.9, which means that our target margin of error should be what? So we're going to take 0.9 and we're going to cut it in half to make what? 0.45. So we can't have 0.45 here. So we're going to have to round it down to the nearest, we're going to round it down to the nearest 0.05, if I am not mistaken. Yes. So we're going to round it down because we can't do halves. So we're going to go ahead and put this as 0.4. We are doing, let me see, we need assurance. So we need our target with assurance. And then additionally, I think we don't need to truncate this one. So this would require 65 people per group. So remember that it's 65 people per group in this instance. So 65 times 4 is 260 people. So to put this into perspective, you're running 260 people. That is a 1-hour session. So that's 260 hours, which is basically about 10 days worth of work. That is many, many, many hours. In fact, let me see how much that would be. Yeah, that's about 37 hours like per week in that case. So you're going to get a pretty good effect here because the Stroop effect is pretty robust, but it looks like it's going to take a lot of work with 4 groups and a between groups design. So now let's focus on the sunk cost effects. This is another between groups design. Here, the effect is small. So our population Cohen's d is 0.3. So we're going to have to round our target of margin of error to, oh, actually, wait, let me see. Oh, that's truncating. We don't want that. We have to actually use the slider. And wait, yeah, never mind. We can do 0.45. So it would actually be 53. So with 53 times 4, it'd be closer to 202 or 212 participants, 212. And that's going to be about 212 hours worth of work. Now, we're going to probably, I don't think we need to truncate for this one, but for this one, with our Cohen's d being 0.3, we're going to have to round it out. Okay, so here's 0.15. So we're going to go ahead and truncate. We're going to truncate this a little bit more so we can actually get the sample size. So if we wanted something, if we wanted to get 0.15 as a target margin of error with assurance, we're going to need, so it's 380, which is 40 volt. And this is a 30-minute session. So that would be about 770 hours worth of work. Becca said, please no. Okay, we have to go to precision. Doing the norm of reciprocity, Cohen's D is about 0.3. So our target margin of error, once again, is going to be 0.15. So we're going for half. We are going to have to truncate our display once again to be able to get a sample size. Our correlation is 0.75. So 2, 3, 4, 5. So with this, within subjects design, we would need 117 people. But this is a 2-hour session. So that's about 234 hours worth of work. So here's the thing. Now, those other examples that we showed, the Stroop and the sunk cost, and here we have the norm of reciprocity. Now that you know all of this, which one do you think would be the best to do? Who says Stroop? Who says sunk cost? Who says norm of reciprocity? Now, norm of reciprocity is about 234 hours worth of work. To kind of put this into perspective though, when we go back to precision 2, and in this case, we're going to 0.45, so we're going back to our Stroop study. Stroop study, here we go. So in this case, 53 times 4, so that's 212 hours. Because with Stroop, you need 212 participants, 53 per group, but that's each of those is only 1 hour versus the norm of reciprocity, which is 2. So it's possible, both of these are pretty close together, but I'd actually argue the Stroop effect's probably the best thing to go with. And here's why. In terms of manpower, in terms of the hours you're going to have to work, these are really similar to each other. This is 212 versus 234, but this is a big effect and you're probably going to get it. You may not get this. So let's kind of work our way through and talk about why I think that. So I would say go with the Stroop. Okay, so the answers were, as we kind of found, 53 per group, so that's 212 total. For the sunk cost, it was about 385 per group, 1540 total, and the norm of reciprocity is 117 total. Now here's where the rest of that comes into play. Angela will need funding for her study. Her university pays participants $10 per hour. For each study, calculate the participant costs. And remember that the projects based on the Stroop task and the sunk cost have 4 groups. They have 4 groups, so don't forget those participants. So we'll go back here so you can see it. So here's the number of participants. And then you can also write this down as well. Oh, wait, there's a marker. There's a marker. So let me see if I can make this a little bit bigger. Let's see if the marker works. Oh, hey. I think this is my pink marker. I think. Let's find out. I mean, it is pink. I'm assuming it still works. So Stroop is 1 hour. Sunk cost, if I am not mistaken, let me go back. Sunk cost is 30 minutes. And then norm of reciprocity is 2 hours. And remember, it's $10 per hour. So for the 30-minute session, you're basically putting that down to $5. Now, when you work out the math that way, which is the better one to do? So it's $10 per hour. So if it's 1 hour, it's $10 times your total number of participants. For sunk cost, it's a half an hour. So we're going to do 5 per the total number of participants. And then for the norm of reciprocity, we're going to do 20 because it's 2-hour study per the 117 participants. Let's see. There. Does anybody need more time to calculate that? So what would you do? You do Stroop. That's what I said. Okay, so here's how we do this. So we have 212 participants. So they're doing 0.5 hours each times $10 an hour. Actually, wait, Stroop was 30 minutes? I thought it was an hour. It is an hour. That's not correct. So it's 212 times $10 an hour. That math should actually be 212 times 10, 2120. So that math is incorrect. So let me fix it right now because it's going to bug me if I don't. 2120. Okay, and save it so it never happens again. So we have 2120. The sunk cost effect, if you weren't already scared off, like if you were hopeful that running 1,500 participants was something that could be done, even when they're only doing it for 30 minutes, you still almost are paying about $8,000. So don't do it. The norm of reciprocity is pretty hopeful because that's a pretty small number of participants. But when you make the experiment very long, that basically doubles the cost. So because of this, the correct answer is to pick the Stroop. And honestly, I would anyway, because between these two are pretty close. But hey, Rachel. No, I know, I saw you. Can I see your health assessment? Cool, thank you. So even though these are pretty close in terms of dollar amounts, I'd say pick the Stroop anyway, because it's a big effect. You're probably going to get something. It'd be kind of bummy if you're wasting this much money, or heaven forbid, this much money on something that is only a moderate effect if you're lucky. So Angela will also need time to run her study. Each participant must be run individually. Calculate the time required. You can already kind of work through that. Remember that the Stroop effect, the study is 1 hour. So we can kind of go back here with 212 participants. The sunk cost effect has 1,540 participants per half an hour. And then the norm of reciprocity is 2 hours. Rachel, you might have missed this. Our next homework assignment, the Chapter 11 handout, since we haven't even started Chapter 11 yet, it's going to be due on the 24th, along with homework number 13. And then your next results and discussion draft that will actually be for points is due next Thursday. And I'm going to start recording these because we have some people that have left campus early. And so we need to make sure that they can access this. So everybody will be able to look at this later, and I'll send a link later tonight. Okay, is everybody good calculating the time? Okay, so it's about 106 hours for Stroop. That's what the half hour, yeah, I don't know why they did that. Yeah, so it's actually 212 hours for Stroop. So it's actually more than 2.5 40-hour work weeks. It's more than that. There are 770 hours for Stroop. That's about 19 work weeks and 234. So the 212 hours for Stroop, that's probably going to be up to 5 40-hour work weeks. This is 19. This is 6. So once again, we're pretty close between Stroop and the norm of reciprocity. 5 weeks versus 6 weeks in the grand scheme of things isn't much. I really miss days when I used to run studies in grad school and it'd take me just a month to collect my data. That was nice because I run multiple people at once. So when you kind of work on this, assuming that she's equally interested in all 3 projects, which would you recommend that she pursue? Does anybody want to look at the sunk cost effect? After all of this, if you still want to look at the sunk cost effect, I am going to tell you, I think you are very, very brave. And also maybe just a little bit passionate about the sunk cost effect, because I don't think anybody who really, you must really love the sunk cost effect to spend the better part of an entire semester, if not a little bit longer, studying that. So it's likely that only the project based on the Stroop effect is going to fit her time and her budget. And this is especially true given the importance of replication. She should manage her project to give her time to replicate any interesting results. And if you're talking about something that takes about 5 weeks to do, that's enough time in the semester where you could plan another study and replicate your findings. So, and also it's a big effect. Odds are pretty good she's going to get something. Okay, so that's kind of an example of how you can use precision for planning before you ever actually conduct a study. And I would recommend that if you are interested in research, that this is absolutely what you should do. So if you have a pen or a pencil and paper handy for your next results and discussion section, I did get asked how many completed it in person and how many completed it on Zoom. I'm happy to report that I have that for you, so please write it down. We have 5 people who did this in class, in person, and we had 6 who did it simultaneously on Zoom. This was an activity, and I don't typically include the activity slides for chapter 10. So this is the end of chapter 10. But yeah, this is an activity and I don't usually include those with the slides because I want us to do it in class. But we are about to start chapter 11 and we're going to talk about correlation. So yeah, here's the bad news. We have to do some more math. But the good news is that calculating correlation coefficients is not that hard. All you need are z-scores. So if you haven't remembered what z-scores are, or it's been a while since you thought about z-scores, well, don't worry, they're coming right back. Okay, so I am saving because I don't want those mistakes in there again. I'm going to go ahead and close out of this for now. We will probably come back to it. We usually do. All right. Okay. And while we wait for that to load, let's look for some fun correlations. Fun correlations. Ooh, here we go. Thank you, BuzzFeed. The 10 most bizarre correlations. Oh, you know this one, ice cream and murder rates. A pirate shortage caused global warming. So here we have the number of pirates. Here we have the average global temperature. I'm not going to read that one. You can read it yourself. My goodness. Anyway, sorry, Dr. Gilchrist is prudish. Eating organic food causes autism. No, it doesn't. That's correlation. So take a look. So because of better diagnostic criteria and better diagnostic methods and increasing awareness, diagnoses of autism have increased. So have sales of organic food. Here's another one. M. Night Shyamalan makes bad movies because people don't buy newspapers. So here's his performance from The Sixth Sense all the way down to The Last Airbender in 2010. I would argue I liked Split, even if not psychologically accurate. I also really love Unbreakable, and Glass made me mad. Glass made me very mad. And then we have total newspaper sales. So by 1999, they're doing pretty well. And then all of a sudden, gee, could it be that there's an additional variable that might explain this? Perhaps the internet, the interwebs. Using Internet Explorer leads to murder. So here, use of Internet Explorer versus the murder rate. Mexican lemon imports prevent highway deaths. So here, lemons imported to USA from Mexico. And here, total US highway fatality rate. So we get fewer lemons imported from Mexico, and we also have a lower highway fatality rate. Obesity caused the debt bubble. No, just both of them are increasing very, very quickly. Facebook caused the Greek debt crisis. Number of active Facebook users, yield on 10-year Greek government bonds. Facebook also canceled out the cholesterol lowering effects of Justin Bieber. So here we have serum cholesterol. You can kind of see it over time. And so those are some really interesting correlations. Now, another one that's kind of come up. So one of the things that's interesting is that I'm sure that you've probably heard, especially very, very early on in the pandemic, that an interesting idea that was going around, and I'm saying idea because, well, it was an idea and it was certainly not a correct one, that 5G was part of the problem, and the areas that had higher COVID spread were also areas that had more 5G towers being erected. Could it also be potentially that there is a third variable that can explain both of those things? There can. It's called population density. Areas that are more dense are probably going to have access to better technology, more 5G towers, and because they are more populous, they're going to have a greater COVID spread. So it's really important to pay attention to when those kind of ideas come out, because they may be correlated with each other, but there may be another variable that is playing a role, which explains all of those fun correlations. So remember, when you see a correlation, keep your thinking hat on. It's very, very important. So correlation. So we're going to talk about a few different things. We're going to talk about looking at data with scatter plots. You are going to learn how to calculate your first correlation coefficient by hand. We're going to actually do a confidence interval on the correlation coefficient. Of course, we would be remiss if we talked about correlation and did not talk about how correlation does not equal causation. And then we can talk about how we interpret different correlation coefficients. So we're going to start by looking at scatter plots to determine if there is a correlation. And while you are writing, I will use my hand cream. I am almost out of my little sample. Today's lecture was brought to you by Luscious Hand Cream Handy Guru Goo. It is very good. My hands are starting to get eczema this time of year, so keeping my hands nice and clean and moisturized is really important, especially in these hand-washy times. Okay, so I want you to imagine, and I think this is something that we can all admit that we've struggled with this at some point or another, body satisfaction. Yay. So let's see, so imagine that you wanted to actually look and see if there was a relationship between body satisfaction and well-being. So one of the ways that you could do this is you could get a metric of somebody's body satisfaction and also get a metric of their well-being. So we can plot body satisfaction on our x-axis. We can plot well-being on our y-axis. So basically, for every person's data point, They have an X coordinate and a Y coordinate. So this one little data point is one person who kind of scored a 3 on body satisfaction and is pretty low in well-being. So each data point is made up of an X coordinate and a Y coordinate. So X and Y scores determine position. So body satisfaction, as you can kind of see, is on a 1 through 5 scale. 3 is kind of our neutral value. And then well-being is on a 1 through 7 scale, with 4 being our neutral value. So if it's higher than 4, well-being is pretty good. If it's less than 4, well-being's pretty bad. Body satisfaction, if it's less than 3, it's not looking very good. If it's more than 3, it's pretty positive. Now, generally, as you can kind of see here, you can overall see that there's some sort of relationship here. You can kind of see that people who feel pretty good about their bodies, by and large, we have a couple of little outliers here, but most of them are increasingly likely to report higher well-being. So higher Y scores tend to go with higher X scores. But as you can see, it's not a perfect relationship. There's a lot of scatter. There's a lot of variability in this figure. And so what you're actually looking at here is a correlation coefficient of 0.47. So this is a moderate correlation. So one of the things that we're going to find with human behavior, just in general, because people are variable, people are different, if you can get a correlation coefficient that's based off of psychological variables that's greater than 0.3, you're doing pretty well. So what we can find is that there is a moderately strong link based off of this data between high body satisfaction and high well-being. So here are a couple of things to keep in mind. The correlation coefficient is just one piece of the puzzle. Even with a strong correlation, you are still going to have scatter. And I'm going to keep repeating this. Correlation never implies causation. Now that you know this, you can take to message boards on the internet anytime that a scientific study is brought up, and you can talk like other people on the internet. But I actually want you to go one step further. So correlation doesn't imply causation. We can't detect here, we can't determine here whether high body satisfaction causes better well-being, or people who have really good well-being also tend to end up liking their bodies as a result. Because we are measuring and not manipulating, we can't actually tell what came first here. And because we can't determine what came first, we can't determine any sort of cause-effect relationship. All right, is everybody good? Does anybody need some more time? Okay. So we measure correlation through a correlation coefficient, which is also referred to as Pearson's R. So this measures, so basically what we kind of do is we are trying to find a line of best fit that basically goes through all of these scattered points while trying to minimize the difference between each dot and that line of best fit. So one of the things that you'll kind of see, so here's a 0.9 correlation. Can you imagine the line that goes through all of these pretty easily? You should be able to, and it almost falls on a perfect diagonal between X and Y. Now, as you kind of see, when our correlation gets more, when it lowers, there's more scatter, and it also becomes harder to draw that line. So I can still draw the line. It's kind of like this, but there's a lot more distance between each point and the line of best fit. By the time that we get to 0.3, there is actually a correlation here, but it really doesn't look all that different from 0, does it? 0.3 looks like, 0.3 basically looks like I took a shotgun and shot it at a piece of paper, and this is what came out, this really scattershot thing. But there is a bit of a relationship here. Notice that in general, as X increases, Y increases a little bit. Now here, 0, a correlation coefficient of 0 is also scattershot, but there's not really the same kind of relationship here. And it turns out with a correlation coefficient of 0, the line of best fit, oh, I forgot I can annotate. I can annotate. I can annotate. Oh, it's amazing. Oh, let's do it. Okay. It's not perfect, but it'll do. And then here, so you can kind of see that the line's getting kind of increasingly flat. So here, I think it's like that, maybe. And then the best line of fit here is just me, nice and flat. I'm actually really proud of that. Okay, now we're done with annotating. Okay, so the correlation coefficient basically fits between -1 and 1. So the number itself tells you about the strength of the relationship, and then whether it's positive or negative tells you about the direction of the relationship. So if it's positive, that means that as X increases, Y increases. As X decreases, Y decreases. A negative direction is going to mean that as one increases, the other one decreases. So for any relationship, we need to see the scatter plot. R can be really helpful, but it doesn't always tell us the full story. So you should try your best to get used to eyeballing correlations. Yay! One of my friends tested negative and doesn't have to quarantine anymore. So if you try to draw a line through some of these points, and like I said, you should try to imagine that, you can kind of see that they fall on a line relatively well. So here are some more scatter plots. You can get a better idea of the strength when you look at the lines. So here is a perfect correlation. There's no scatter here. Everything falls on a line. Like, isn't that really beautiful? Well, I hate to break it to you, if you're looking at psychological variables, this is never going to happen to you, ever, ever. That's a promise. So this is a perfect correlation. There is no scatter here. Here is -0.6. So here, as as X increases, Y decreases. So again, I'm going to go ahead and annotate. We're going to draw some lines. Let's go ahead and draw a line this time. I think I'm going to use green, my favorite color. All right, so you can kind of see the line kind of looks like that. And then here is that 0.9 that we saw, but this has a regression line drawn through it. So I thought about whether or not I should not teach you regression, but honestly, regression is based on correlation. This little line of best fit that I'm trying to draw and the one that's right here, these are regression lines. They help you make predictions based on correlational data. So the regression line tells us what Y value is most likely associated with some X value that we would be interested in. So for correlated variables, a regression line can actually be really helpful because it enables us to make predictions. So the idea basically being, if I have a regression line and I have an X variable and I have a Y variable, if I know what your X is, I can just go up to that regression line and make a pretty good prediction about what your Y variable is going to be. So when we're trying to do things like admissions data, and we're looking at things like your GPA and your test scores, we actually, a lot of people actually make predictions on whether or not you will succeed based on how well your GPA fits on a regression line. So they plug in your GPA, they put it on that regression line, and they make a prediction about how you're going to do in school. The same is true for SAT scores or other college entrance exams. So we like to rag on correlations because I'm like, you can't experiment with correlational data, but correlations still have their place. They enable us to make predictions. So here's something really critical. Pearson's R only examines linear relationships. So here we are looking at some data between room temperature and rated comfort. And notice that we've got a really pretty U-shaped curve. Now, I like that data. The problem is, if I try to get a correlation coefficient for this data, here's what my line of best fit looks like. We're going to do pink this time. So if we do a correlation coefficient, here's my line of best fit. Now, is that an accurate representation of the data? Absolutely not, because remember, Pearson's R is always looking for a line of best fit. This is what is called a curvilinear relationship or a quadratic relationship. It's a parabola. It's a quadratic relationship. So if you're solely looking for the line of best fit, the problem is that in this instance, you're basically gonna underestimate the relationship and not fully capture what is going on here. And in that case, you would probably want to do a quadratic or a curvilinear regression of some kind that can accurately assess this curvilinear relationship. Now, on the other hand, now this one I'm gonna have to draw because there's no way around it. So here we have high school GPA and driver knowledge test. And you can kind of see that the relationship is, well, I want to say it's exponential, but it's more of like a power function. And so in this particular instance, yeah, I know that's a terribly drawn line. I did my best. Scores on this test kind of max out at 30. This is a ceiling effect. Basically, if you're getting over a 2.0 GPA, you are basically acing this test. Most of the students score very high. This is actually a 0.76 correlation, but because of this ceiling effect, we are restricting the range here. We're not actually getting a true relationship between GPA and driver knowledge because everybody above a 2.0 or a 2.5 basically maxes out at 30. The test is too easy. So this is why looking at the scatter plot is so important, because if you looked at just these, you would completely fail to understand what is actually going on in your data. So I always like graphs. I always like tables. These statistics can be really important, but because they are based on linear calculations, if your data is not linear, they're not telling you the whole truth of your data. So do keep that in mind. Uh-oh, we got to clear our annotations. All right. That looks much better. Additionally, if we're looking at the tightness of points, that can help us figure out what our correlation coefficient is. So the tightness of the points to that imagined line can also help us figure out what our correlation coefficient is. The more tightly grouped together your data points are, the higher that correlation coefficient is going to be. Another thing that you can actually do is cross through the means of your X component and your Y component. So here we are kind of looking at 4 different quadrants. So the vertical line right here is at the mean of X. The horizontal line is at the mean of Y. So points can be matched in quadrants. So X is high, it's above the mean, and Y is high. Here, X is low and Y is low, or they're mismatched. So this is an instance where X is low, Y is high. Here is an instance where X is high and Y is low. So the idea here is that you can look at the ratio of how much are matched and how much are mismatched to get an idea of what this correlation should be. More matched than mismatched suggests that it's positive. More mismatched than matched suggests a negative. And if they're all equal, you have no correlation. So if you have an equal number of matched versus mismatched, you've basically got nothing. So mostly matched or mostly mismatched points suggest a stronger correlation, but if they're more, so notice that these, most of them are falling in this quadrant or this quadrant. We have considerably fewer that are mismatched. Take a look at this one though. Here, the mismatched quadrants, there's more data in here. And additionally, notice that there's a lot less of a tight scatter. So this is probably going to be a weaker correlation than this one. So here's kind of an example. So take a look at our nonlinear relationships that we talked about before. So the reason that this kind of messes up the relationships, there's an equal distribution of the data in all four quadrants, which basically means that a correlation coefficient is going to underestimate the relationship that is actually there. On the other hand, if we're talking about this, does anything look really off to you about the our driver's knowledge data and GPA correlation? Huh? The density pulled your Y mean up. So notice that we have a lot that are matched. We've got some that are mismatched, and we've got nothing here, and that is creepy. It's not creepy in terms of like no data should ever look like that, but if I'm looking for a linear correlation, I need some data here, and I got no data here, and that's just not right. So now we're going to talk about how to calculate Pearson's R. So we're going to talk some math, but I promise it's not scary math. I mean, I know what some of you are going to say, Dr. Gilchrist, all math is scary. And to that I say, have you ever considered the possibility that math is more afraid of you than you are of it? That's what my mom tells me about snakes. I don't know if it actually works with math. Okay, so let's go back to our Thomason critical thinking study. So again, just to remind you of how the study went, Thomason basically studied whether critical thinking could be a useful intervention for teaching people logic problems. So he basically, this researcher basically gave a group of 12 participants a pretest. In this case, it was composed of LSAT questions, and the LSAT is an entrance exam and an aptitude exam for law school, and it's basically a bunch of logic problems. And then Thomason and colleagues basically then gave people this critical thinking seminar and this workshop, and then they got a post-test, more LSAT questions. So here's our data. So correlation is really important for pre-test, post-test designs. If we want to make sure that we get the effect that we want to make sure that the pre-test and post-test performance are at least somewhat correlated with each other. And ideally they should be, because each person is giving their own pre-test and post-test, so they should be correlated. And we do know that they have a pretty high correlation. So here is our correlation coefficient, 0.89. That's pretty solid. We like to see this. So what I'd like you to do right now, I'd like you to try to go to our battle of the quadrants, and to kind of help you out, one of the nice things about doing Zoom, I can draw the lines for you. Isn't that nice? Okay, so it's 0 through 18. So here's kind of our midpoint. I'll try to keep it straight. Okay, and it's 0 through 20, so our other mean is here. It's not perfect, but it'll do. Yeah. Oh, no, undo, undo. Let's try that again. I wish I had a mouse and not a silly trackpad. Okay, so here we have our quadrants. So let's go ahead and kind of see what's going on here. So as you can kind of see, so we've got more matched quadrants than mismatched quadrants. This is partially how I drew this line. This would probably be in this quadrant. This kind of looks like it would be in this quadrant. So we have some pretty interesting data, and you can kind of see that there's very few areas of mismatch, which means that this is a pretty tight correlation. You can almost see the line drawn through the data here. So to examine this quantitatively, we now need to take each of these x, y coordinates and convert them into z-scores. So here's what we're going to do. Oh, I need to get rid of my annotation. So actually, there is a little bit of a mismatch here. They draw this for you, and I actually needed to do it through the mean of this. So my crosshatch was not correct. The crosshatch needs to be through the actual mean of the participants' scores and not the mean of the quadrant. So when we actually draw it, there are some mismatched areas, but here's what we need to do. So let's just go through a quick reminder of how we get a z-score. So just as a reminder for you, a z-score, so if we want the z-score for the x component of a given coordinate, so we're going to have our z of x, and yes, that's what we call it. We call it z of x. Z of x is basically that person's x coordinate minus the mean for x divided by the standard deviation for x. The z of y equals y, so that person's y coordinate minus the mean of y over the standard deviation of y. So it is math, but it's not scary. It's hopefully not that scary. Nobody has to take a derivative or anything like that. So for example, now here's where it does get a little trickier though. ESCI will calculate each of these for you. So you can do this in ESCI. I believe in the first handout though, I do actually make you do it by hand. So we get all of our scores. We have the z of x, the z of y, for each participant, and then you have to multiply those together. So we get zx multiplied by zy, and so that's how we actually end up calculating our Pearson's R. Our correlation coefficient is made up of the sum of all of these values, z of x times z of y for each person, and all of that is divided by n minus 1. So in this case, that would be 11. Does this seem like something you would be able to understand and do? Does anybody have any questions? Okay, let's go ahead and mess around with ESCI just so we get a better idea. ESCI. All right. So ESCI will do all of this for you. So this is in the scatter plots tab. So here's our Thomason data. We will go ahead and not look at that data, so I'll kind of increase just a little bit. So here we have our Thomason data, and where is it? So we have a cross through our means. We want to display our p-value, and we can also do a scatter plot of z of x and z of y. Why aren't you calculating it? What's going on? Why can't I do it? Let's see. Enter your own data. Oh, here we go. I have to click show z-scores. Okay, so one of the things that you have to know is that you're going to need to get the mean and the standard deviation for X and for Y. So our mean for X is going to be 11.58. Our mean of Y is 13.25. Our standard deviation for X is 3.315. Our standard deviation for Y, and I'll go ahead and zoom in a little bit, is 2.895. So when we are calculating Z of X and Z of Y, this is what we're basically doing. So here, our X is basically going to be 13, so this person's score, minus 11.58, and it's divided by 3.3, so you get 0.42. This person has a post-test score, so this is their Y component of 14. So it's 14 minus 3.25 divided by 2.89, which leaves you with this. And when you multiply 0.42 times 0.25, you get 0.11. So here actually are the scatter plots of ZX and ZY. And notice that they look really similar to our scatter plot, except now they're expressed in standardized scores. So we add all of these up, and this is how we get our correlation coefficient. Now here's what you'll notice. Our mean is 0 for both of these. Now why would our mean be 0? Because when you put in standardized scores, 0 is the mean. And our standard deviation is 1. And that's because we've put it into a standardized format. Additionally, here you can see areas where we kind of have mismatch. This one's positive, this one's negative. And remember that if it's negative, that score is lower than the mean. So here we have some areas of mismatch. So this score is 0.12 for X, but it's negative for the Y. So we can actually see our areas of match and mismatch here as well. So let's go ahead and zoom out and see if there's anything else. So we can actually also reveal our regression panel. So we'll kind of talk about this more in the next chapter. So it basically says I can display a regression line, check it out, and you can tell the line of best fit, that's pretty close to being almost a perfect diagonal line. And so what we've basically done is picked a line that minimizes the distance between each point and the line. So this is the regression line. We'll talk more about what this means next time and what a residual is. And now I'm getting flashbacks to first year of graduate school, and now I'm scared. Okay. So this is pretty straightforward how we kind of get this. So we get a z-score for each x coordinate. We get a z-score for our y coordinate. We multiply that together per data point. So each person's data, and then we add up all the multiplications. This is one of the easiest things we can do. So this is how we get that 0.89. We add all of these up here, and then we divide them by 11 and minus 1. Now, one of the things that I want to mention is that outliers are always going to drag your correlation coefficient around. So I want you to imagine that we had a participant who did really poorly on the pretest, but they did really well on the post-test. Now, if you saw this on a scatter plot, you would start to wonder if there were some issues with this participant, if there was an issue with the data entry, or something else that could have led to that happening. But what if you're only seeing the correlation coefficient? Would we be able to tell anything about an outlier when we only have the correlation coefficient? No, absolutely not. So we're going to talk about the influence of outliers on R here. So I'm going to go back into ESCI after I closed it out, but it's right here, so I don't mind. So we're going to go ahead and go back into our scatter plots. So here, so it only goes up to 20, and I'm going to keep it that way. Your slides show 30. Let's go ahead and do it that way too. Why not? So let's say that we have participant number 13. They take the pretest and they ace the post-test. Take a look at that data point and look at what just happened to my correlation coefficient. Look at what just happened to my correlation coefficient. So that line of best fit is still there, but once I take an outlier, it completely pulls my correlation up, because we have to have a line of best fit that accommodates this point. So it drags the entire correlation down. And we can actually see this in terms of our z-scores. So you can kind of see our other z-scores are still kind of largely the same, but here's the problem. Notice how they've changed because our means have changed. So let me get rid of these for right now. So we go back to the original. Okay, so notice. So I want to pay attention to this first data point, which is kind of right. It's very nicely kind of in the middle here. Let's see, where's point 1? Point 9, point 12, point 11, point 12, point 13, 14, 15. Oh no, those are just all the data points. Okay. Wait, here's one, I think. Maybe you? No, you'd be up here. 13, 14 is what we want. So you're probably right here. Yep, there it is, 13, 14. So this is this data point for the first person. They're right here. So their z-score in relation to the mean is 0.42. Their z-score in the relation to the mean of y is 0.25. Now let's put that 3 and that 30 back in. And look at how the z-scores change, because this changes the mean for both the x and the y coordinates. So it goes to 0.52, so it doesn't change too much in x, but having that massively high number of 30 actually makes it negative. It is now below the mean when previously it was above it. And because the mean has changed so much, remember that the mean is absolutely dragged around by outliers. So this is going to affect how you calculate your z-scores. And because we're drawing a line of best fit, let's go ahead and take a look at that regression line, shall we? And also, let's put a cross through our means. Look at how different it is now. None of these were in this mismatched area. And this one is mismatched as well, but it's very, very high. So let's go ahead and look at what happened to my regression line. As a result, it was positive. Now it's actually shifted slightly negative because of this very high mismatched value. And because of the modification in means, we have more mismatched than we have matched. So yeah, you should always take a look at a scatter plot before just trusting a correlation coefficient. Having good pictures can be helpful, because calculating your correlation coefficient is based on the means and the standard deviation, both of which can be dragged around by outliers. That means the correlation coefficients can be dragged around by outliers. Okay, so always, always, always look at the scatter plot, because R is only going to tell us how linear the relationship is. So here's kind of an example. Let's take a look at studying reading scores of children at age 6 and age 9. Here's the plot. So what do we think about this plot? So here's the reading score at age 6. And then here's the reading score at age 9. What do we think about this? Does it bother anybody that we don't really have a lot in this mismatched column? It really shouldn't. I don't think I've ever seen anybody who was a really good reader at 6 and then suddenly became a bad reader 3 years later. That generally does not happen. So there are 3 kinds of scorers here. So we have people who are low at 6 and they're still low at 9. They're low scoring at 6 and then high at 9. So maybe they just needed more time and more practice. And then people who were good readers when they were 6 and they're still good readers now. But obviously, we don't really see high scoring 6-year-olds reading worse at 9. It looks like a less extreme version of the high school GPA and driving knowledge test. I'm not saying it's necessarily a ceiling effect, but we're not going to see something like this because generally, I think the one thing that could potentially make that happen is something like severe brain damage, and that's pretty rare for a child. So generally, once a child knows how to read, they're going to be able to read on future tests. So looking at the scatter plot is always really important. Additionally, I may have talked about this a little bit last semester when we talked about something called range restriction, but we have to talk about the range of possible values. So range restriction occurs when X or Y values don't show the full possible range. So for example, if I'm looking at the relationship between SAT scores and GPA, but I'm only looking at students who got a 3.0 or higher, I am going to have a restricted range that may not tell me the full story of the data. So here's one example. So Richardson and colleagues back in 2012 looked at a meta-analysis of high school and college GPA. And generally on average, the correlation wasn't bad, but it's probably a little bit weaker than you'd expect. And I know what some of you are like, Dr. Gilchrist, I was really bad in high school and I'm really good in college, or I was really good in high school and I'm really bad in college, or we're kind of all over the place. So it's not like a super strong relationship, but it is a positive one. So here's the data. So let's say, so here's all of the data right here. So this is why we get 0.4. There's a lot of scatter here. Now, here's what's interesting. If we only look at the correlation of students who were basically the top 20% in their class, that correlation disappears. The correlation between high school GPA and college GPA is only about 1.13 at that point. And this is what happens with range restrictions. So if a college only accepts the top 20% of applicants at that point, high school GPA is no longer a very good predictor of college GPA. So when we restrict the range like this, we actually underestimate what's really going on in the population. That's why people who go to, it's why you can't really predict college GPA from people who go to Harvard. They're all the best in high school, or at least have the most access, which can occasionally lead to really good GPAs. But it's not a very good predictor of how they will do in college. On the other hand, if we're looking at a place that is more variable and takes a wide variety of people, such as Cotty or a big state university, you're probably going to see a stronger correlation between high school GPA and college GPA, because that range restriction doesn't exist to the same extent that it does at hyper elite, like best of the best colleges. All right, folks, so that is all I had today. Hope you don't actually have a quiz due this week, but I will go ahead. If you missed turning in your Chapter 11 handout, or if you need more time, I will take it until the 24th, and the same is true for your next homework assignment. So thank you, folks. Have a wonderful day. Stay safe. Stay smart. Email me if you quarantine or if there's anything you need. I'm happy to help you out. And I will see you all on Tuesday. Have a good weekend. Make good decisions. Don't lick doorknobs. Y'all know the drill.
Thank you.